Hello, this is Jack Jackson back again, and we're going to continue our series of videos going back over and reviewing some of the concepts from this playlist and this talk about derivative concepts. And so I'm going to ask you a few questions here as before, ask you to pause, write down your answers, and then hit play to go back and check your answers. So I'm going to ask you now a series of questions about the relationship between the graph of y equals f of x and the values on the graphs of the first and second derivatives. So we're going to how these graphs relate to each other. We did a little bit of this talking about at the end of the last video with this picture up here. Okay, what does the graph of a function which is differentiable at a point look like when we zoom in close to that point? Okay, press pause and answer this now. Okay, hopefully you've written down an answer to that. What does the graph of a function which is differentiable at a point look like when we zoom in close to the point? Well, a couple of things happen. First of all, if the derivative is defined at a point, then the graph is continuous, so it's one connected piece, nearby at least, with no breaks of any kind. It's also smooth, which means it has no sharp corners. If we zoom in near the point on the original graph, it will look approximately like the tangent line to the graph at that point. So that will be, and it won't be a vertical line either because it's a tangent line that actually has a slope. So the short answer is it looks like a non-vertical line as you zoom in close. Now, what does the sign of the first derivative tell us about the graph of the original function? Be as specific as possible and list all the remember there are three possibilities for the sign, positive and negative and zero. So be sure you cover all those different cases so you can be as specific as possible. See if you can write this down and then come back and check your answer to that. Press pause now. Well, let's see here. The derivative tells us the slope of the original curve at each point on the curve, that is the slope of the tangent line. So the sign of the first derivative tells us about the direction of the graph of the original function. So if we want to be specific here, if the first derivative is positive at a point, then the original function is increasing at that point. By the way, be careful when you're writing these things down that you don't use pronouns. Be sure you don't say it or something like that because we don't know whether it is talking about the derivative or the original function, or later on maybe the second derivative even. Okay, but if the first derivative is positive at the point, meaning its y values are positive, which means its graph, that means the graph of the derivative is above the x-axis, then the original function is going to be increasing at that point. If the first derivative is negative at a point, then what's going to be the graph of the first derivative? The first derivative is going to have a graph below the x-axis. But what does it say about the original function? Well, the original function is decreasing at that point. So if the first derivative is positive, the original function is increasing. If the first derivative is negative, then the original function is decreasing. And that it kind of goes both ways. If the original function is increasing at a point, at a single point, then the first derivative is positive. If the original function is decreasing at a single point, then the first derivative is negative. Now, the other possibility is the first derivative could be 0. Now, if that happens, then the original, of course, that means the graph of the first derivative is on the x-axis. But what about the graph of the original function? Well, the original function then has a horizontal tangent line at that point. We call that a stationary point. So this point might be a local extremum. So it turns out that if the second derivative is negative, then the graph is going to be concave down and at a local maximum, and it has a horizontal tangent line. That makes it be a local maximum. Similarly, it's a local minimum if the second derivative is positive and the first derivative is 0. So first derivative 0, second derivative non-zero, then that makes it a local extremum. Specifically, if the first derivative is 0 and the second derivative is negative, the point is a local maximum. If the first derivative is 0 and the second derivative is positive, the point is a local minimum. However, if the second derivative is also 0, in other words, both the second derivative and the first derivative is 0, it could be a local extremum, but it could also be an inflection point. It's inconclusive at that point. You need a little bit more information, like something about the signs of the derivative or possibly the signs of the second derivative on either one side or the other, well, really both sides of the point, and you can find something out. Now, if we sort of reverse this last one, if a function has a local extremum at a point, then the derivative must either be 0 at that point or the derivative is undefined. So if you're looking for a local extrema, a local maximum or local minimum, or just local extremum of any kind, you're looking for all of those, local extrema, plural, then what you want to do is take the derivative, set it equal to 0, solve that equation, and any of those x values are potential local extrema. Also, any place where you have the derivative is undefined is there. And there is one other possibility I guess I should also put here. Or the function is at an end point. Okay. What is the sign of the second derivative? What does the sign of the second derivative tell us about the graph of the original function? So up here we talked about what does the sign of the first derivative tell us about the graph of the original function. Now tell me what the sign of the second derivative tells us about the original function. See if you can write that down. Again, be as specific as possible, so include all the cases of the different signs that the second derivative might have. Write those down and then check your work with the video. You should be able to do this from memory. This is basic stuff that's very important about derivatives and second derivatives. Press pause now. Well, the second derivative tells us the concavity of the original function. If the second derivative is positive, okay, then the first derivative is increasing and the original function is concave up at that x value. Okay, if the second derivative is negative at a point, the first derivative is then decreasing and the original function is then concave down at that point. All right, well, what's the other choice? Positive, negative, the other choice is 0, or I guess undefined. So if the second derivative is 0, okay, then it turns out that you could have a point of inflection or inflection point there. So if the first derivative is non-zero and the second derivative is 0, then the original function has an inflection point. And as we said just a little while ago, if both the first derivative and second derivative are 0, then the function will either have a local extremum or it might be an inflection point, but we need more information to determine which. Now flip that last statement around backwards and we can say this: if the original function has an inflection point, then the second derivative is 0 or undefined at that point. Alright, now look at this situation here and see if you can tell me something about the graph. And then maybe graph the relevant portion of such a function. So we want f of 3 to be equal to 5, f prime of 3 equals 0, and f double prime of 3 equals 2. Could you graph such a function? What do each of these things mean? What does f of 3 equals 5 mean? What does f prime of 3 equals 0 mean? What does f double prime of 3 equals 2 mean? And what if you put all those together, what can we conclude about the graph? See if you can think about that, work it out, come back when you're ready to go on. Press pause now. Okay, well, first of all, the fact that f of 3 equals 5 just says that the point 3, 5 is on the graph of the original function f. So we know a specific point on the graph. So we're talking about the graph at the point 3, 5, and we want to see what's happening near there. Next thing, just the fact that f prime of 3 equals is defined, okay, means the graph of f is defined and continuous, and it looks like it's tangent line, then that tangent line has a slope of 0. So nearby, that function looks like a horizontal line. So if we zoom in close, it should look like a horizontal line there. Now this is possible that it could be an extremum. The only way it wouldn't be an extremum is if the second derivative was also 0. Then we might have a problem. Then it could possibly be an inflection point. Well, since the second derivative is not 0, in fact, the second derivative is positive. That's the main thing I want to get out of that. Then the original graph is concave up at that point. So think about it. It's concave up, but actually horizontal tangent line. That means we're at the bottom of that concave up piece. So in fact, this point 3,5 then is a local minimum. So it looks something like this, a local minimum at 3,5. Roughly something like that. Okay, so in the next video, we're going to talk a little bit about using the definition of the derivative, no shortcut formulas, to find the formula for a derivative function, use it to evaluate exactly the derivative at a point, look at some graphs of the tangent lines, figure those formulas out, and look some more at this interplay between and among the graph of the original function, the first derivative and second derivative.